Just in time. Right. I just want to highlight a few things on herbicide selectivity. I want to focus on the commonly used herbicide, which is atrazine. So, atrazine metabolism and selectivity. Atrazine is widely used to control weeds in maize. Now, usually, these herbicides contain chlorine. So, we have chlorinated triazines, which can undergo hydrolysis at the chlorine atom on carbon 2 or on C2. So normally Cl is replaced by OH. Remember, this reaction in most cases is catalyzed by cytochrome P450. But as far as atrazine is concerned, this process is catalyzed by benzoxazinone, that is the enzyme, or dimboa. So hydroxytriazine formed has no herbicidal activity. So what happens? This is the molecule of atrazine, and this is the Cl, which is converted to OH, and dimboa is the is the catalyst for this reaction, or we can just simplify it like this. The other processes are the removal of the alkyl groups, the amine groups. So we have N dealkylation. Now we've got the amine group at carbon 4 and carbon 6. So there are two positions where N dealkylation can occur on atrazine molecule. So the functional groups are removed from the atrazine molecule. These are sorry for the interruption. So these are the groups which are involved in any dealkylation at two positions: NHC25, NHC3H7. So these are the positions which are affected. The first one can be converted to an amine, then the second one again to an amine. You can see I've put P450 question mark because it's dimboa which facilitates those changes. Or we can simplify any dealkylation using this process, because we may not remember this whole structure which we represent by R. Another thing which can happen is that atrazine can be transformed by glutathione conjugations. And you have got glutathione S transferases, which are the enzymes which allow glutathione to conjugate directly with the atrazine. And of course, there will be loss of herbicidal activity. This could be the atrazine molecule carrying the chlorine, and you have glutathione with this structure SH going straight for the chlorine, and you have this structure being formed, which can be moved to the vacuole. This is the simplified version. If we can represent atrazine with this structure, then this is glutathione, having these amino acids, glutamate, cysteine, glycine, and the SH attached to the cysteine. And of course, this SH will link up with the atrazine at the Cl, forming this structure. And this is glutathione as a transferase enzyme which catalyzes this process. So we can also have glucose being involved, where we have glucosyl transferase catalyzed reactions. So glucose will combine with the OH group after hydroxylation in phase 1. Glucose could also combine with amine group after dealkylation in phase 1. So more glucose could be added to glucose atrazine to form joint biocides, where you have glucose atrazine formations. So this is how atrazine can be detoxified, probably in maize, to achieve selectivity. So we can move on to other herbicides which are applied in a state which is not toxic, but the plants can convert them to toxic products and get killed. We have got herbicides which are formulated, which are made as 2,4-DB and MCPB. These products are not phytotoxic, but if they undergo oxidation, which is in this case beta oxidation, they are converted to 2,4-D and MCPA, which can kill. So plants which convert these products very fast are killed. And those with the slow conversion will survive. So this is how selectivity can be achieved in that case. So this is an example of 2,4-DB. It has got the double CH2 here. After beta oxidation, this is removed. One of the, these two are removed, leaving 2,4-D being formed. And this is toxic. 2,4-DB is non-toxic. I also want to talk something on cephanas. Now, there are some grass killers which can potentially kill crops like maize and sorghum. This group of herbicides are known as thiocarbamates and chloroacetamides. EPTC can potentially kill maize, but the manufacturers have added a safener which protect maize. It's known as diclomid. So diclomid is mixed with EPTC before it is sold. And it is part of the herbicide formulation to protect maize. We have got another safener known as Concep, which is mixed with the metallaclo jewel, so that you can use it on sorghum so that it doesn't kill sorghum. So if you were purchasing the herbicide to kill grasses in sorghum and you just buy jewel from any one of the suppliers, there's a possibility that you can kill your sorghum if that jewel lacks Concep. So make sure that if you are going to use jewel or metallaclo in sorghum, that jewel should contain Concep, which will allow selectivity in sorghum. Anachrolaso, which is also a common herbicide in Zimbabwe, we can also use it in sorghum. It has a protectant or a safener known as flurazole. If that anachrol lacks flurazole, you should not use it in sorghum. Then acetaclo can also be used in sorghum, but it should contain oxabetrinyl as the safener or protectants. So please note that most of the grass-killing herbicides, which we may use in maize and sorghum, should contain safeners to protect the crops. So how does the safener protect the crop? Safeners may increase the metabolism of the herbicide. That is the breakdown of the herbicide. They may increase levels of glutathione and the glutathione is transferase, which can detoxify the herbicide. Alternatively, they may increase cytochrome P450 enzymes, which can facilitate oxidation of these herbicides. Now, I just want to talk something on the antagonists. Now, we may use Basagran to control weeds in soybean, but Basagran can only control broadleaves. And on the other hand, you can also use Fusilade to control grasses in soybean. So if you have got a mixture of broadleaves and grasses, it may make a lot of sense just to tank mix Basagran and Fusilade and spray. But if you do that, there is not going to be weed control because Basagran is antagonistic to Fusilade. So some herbicides, when applied as mixtures, have reduced the activity. So in other words, what you have to do is to apply Basagran on its own You clean the tank, you now put fuse red or vice versa. But put one herbicide at a time and make sure that your tank is clean before you put another herbicide. Otherwise, there could be antagonism. There's also synergism or synergies. In this case, some herbicide effects are increased by the presence of an insecticide in the mixture. Probably you are applying insecticides in your field. You may think that you may cut cost by applying the herbicide and the insecticide at the same time. For example, a combination of nicosulfuron plus organophosphate, insecticide could lead to crop injury. So it's important that when you are using your insecticides and herbicides, make sure that after using the insecticide, you thoroughly clean the tank before you use the herbicide. So I'll just give a summary of what we talked about. Yeah, we talked about differential penetration, differential translocation, compartmentalization, sequestration, altered binding site, differential metabolism, which has got phase 1, phase 2, phase 3, and conversion of herbicide from non-toxic to toxic form. Safeners or protectants, antagonists, then synergists. So this is it on selectivity. I should stop